This video will be about exponential growth and decay. In problems that are modeled by exponential growth, we can model a function y equals a times 1 plus r to the power of t. So here we have a represents the initial value, r represents the rate of increase expressed as a decimal, t represents the number of time units that have passed, and y represents the value after t time units. So we can use our formula for things like having interest in a bank. So if we say that we initially put in $A into the bank, we have an interest of 3% compounded monthly. Then we can model our amount of money in the bank as y equals a times 1 plus 0.3 to the power of t, or a times 1.03 to the t, where t equals the number of months that have passed. So in the previous cases, what we had was something where y increased r% each time step, where each time step is a discrete unit of time, such as a month or a year. However, often in real life, we don't have discrete time steps, and instead, things are constantly or continuously increasing at an exponential rate. In this case, what we have is something called growth with base e, and these can be modeled by the formula y equals a e to the rt, where a again is the initial value, t is still time, y is still the value after time t is passed, and here r, instead of being a percentage rate of growth, it just has something to do with the rate of growth. We can see how this works by using our example with a bank again. Let's say that at time t equals 0, we put in $A into the bank. And now, instead of interest being compounded monthly, we have interest continuously compounded. So now, our formula can be written y equals a e to the rt. Often, when describing r, we use a value that tells us how long it would take our money to double. So for example, if we were given that it takes 3 months for our money to double, then we could find r by saying after 3 months y would equal 2a, or 2 times the initial amount. That equals a times e to the r times 3. So then we can cancel out our a's, and what we have is 2 equals e to the 3r. And then using logarithms, we can solve for r. And once we find r, we'll just plug it back into the original equation. Exponential decay is very similar to exponential growth. So the first formula we can define for exponential decay is a times 1 minus r to the power of t. All of the variables stand for the same thing as they did before. The only difference is now we have a minus r instead of a plus r. So this is used in cases where y decreases r% each time step. And then we have our base e counterpart for decay, whose formula is y equals ae to the negative rt. Recall that with exponential growth, we often define something in terms of how long it takes the initial value to double. With decay, our population is decreasing, so instead we'll look at how long things take to have. And in things like radioactive decay, we often call this the half-life.